So I'm going to talk about scalable multi-party computation from nonlinear secret sharing. This is joint work with Sanjam, Abhishek, and Pratay. So just a customary MPC, first few slides about MPC. Like here we have a bunch of parties, each hold input, and they collectively want to evaluate some function f. And MPC protocol should evaluate this protocol correctly. And on the security side, if a subset of these parties are corrupted, then the view of these parties should be indistinguishable from the ideal world where they're only interacting with a trusted party. So in this work, we're only going to be focusing the following setting. Here we have an honest majority. That is, the adversary can at most corrupt less than half the number of parties. And we're in the information security setting. And we are only going to consider semi-honest adversary. So a very basic and simple setting. And our objective here is to minimize the overall computation and the communication complexity of the MPC protocol. In particular, what we want is the following. Suppose the function we're trying to evaluate is written as an arithmetic circuit C over some field F. We want the collective computational complexity of all the parties should be comparable to order of C, the circuit size, number of field operations. And note that this is the optimal we can hope for because even insecurely evaluate such circuits would need this much field operations. And this kind of MPC protocol achieving this level of efficiency is commonly known as a scalable MPC protocol. Here, scalability means that the overall complexity doesn't grow as the number of parties increases. Okay, so why do we care about scalable MPC protocols? So there are many reasons. First, the most efficient MPC protocol in practice are mostly information theoretic MPC protocols because they only involve cheap field operations rather than expensive cryptographic operations. And since the overall complexity of the MPC protocol doesn't increase as the number of parties drops, you can implement such protocols with many parties, and this has many advantages. For example, you might have a very large computation, and you can deploy an MPC protocol among many parties so that the per party workload is reduced to a small amount. And also, the honest majority assumption is more likely to hold in practice when the number of parties increases. And also in some other settings that these kind of many participating parties is a necessary condition for these application scenarios. Okay, so hopefully I have convinced you that scalable multi-party computation is an interesting thing that we should care about. Now, what do we know about how to build such scalable MPC protocols? So based on a very amazing sequence of works, the current state of the art looks like roughly the following. So first, if you want to evaluate a structured circuit, for example, a same D circuit, which is just the same copy of the circuit many times, if you want such a batch of circuit, then you can do it in achieving scalable efficiency. And a recent work by Beck et al. Also extended to a larger family, which they call highly repetitive circuits. On the other hand, if you want to evaluate this develop protocol for arbitrary circuit, for general circuits, then there are essentially two ways of how you can achieve this. The first is a line of work initiated by Damgard et al., which involves a circuit transformation step that transform a general circuit that you want to evaluate into a new circuit that has some specific structure. And after that, you can perform a scalable MPC protocol for that transformed circuit. However, this circuit transformation will introduce some overhead that is polynomial in the logarithmic in circuit size and D, which is the depth of the circuits. On the other hand, the recent work by Goyo et al. Introduced some technique called shared transformation that allows you to do the scalable MPC without this circuit transformation step. And however, they can only achieve the communication complexity to be order of C field elements. On the computational side, they still need the overall computational complexity n into the circuit size C. So this begs the following question. Can we build a scalable MPC protocol for general circuits where it achieves scalable efficiency in the computation complexity? And in this work, we obtained the following results. Suppose we have a field F that is exponentially large. And then for any general circuit over this exponentially large field F, we can build a scalable MPC protocol among n parties such that the communication and the computation complexity measured at the bit level is order of C into log F. So here that means the overall communication of all the parties is C into log F many bits, and the computation done by all parties is also C into log F many bit operations. So how large does this F needs to be? In the protocol, in the paper, we prove that it can be proved to be secure if this log F is comparable to the quadratic number in the number of parties. However, we also conjecture that the protocol is secure as long as the field size is linear in the number of parties. So just a few quick remarks about our results. First, normally in the MPC literature, you measure the complexity at the field level and how many field operations each party did. Here, our result measured the complexity at a bit level, where we are measuring how many bit operations each party did. And as you will see shortly, that this is inevitable for us. And the second thing is that in the paper, we also extend our result to the dishonest setting, assuming a pre-processing model. So in the talk, I won't be talking about it, but I will invite you to look at the paper. So one distinct difference between our work and the prior work is that normally in MPC protocol, you only require the field size to be larger than the number of parties. Here, we require an exponentially large field size. So you might wonder whether this is only of theoretical interest, or are there real-world application scenarios where this is relevant. So in fact, if you consider any MPC protocol for computing the cryptographic tasks, such as the proof generation of a snark proof, it turns out that for all these protocols, these arithmetic circuits that you want to evaluate are naturally over an exponentially large field where log F is, let's say, the security parameter. And in this case, especially if we can prove the conjecture security of our protocol, then we can easily evaluate, implement such protocols for these kind of MPC tasks with around 100 to 200 parties, which is quite practically relevant. Okay, so now let me get into the technical part of the talk. In order to introduce what we do, let's first recap what does the normal secret sharing-based MPC protocol does. As a standard way of doing secret sharing-based MPC, you start by secret sharing all the input wires, and then you emulate the circuit gate by gate. Here, suppose you have an addition or multiplication gate, you locally add, each party locally add or multiply their secret shares to obtain the secret share of the output gate. And if it's a multiplication gate, you also need a degree reduction protocol that reduces the threshold of this secret share of the output wire from degree 2t to t, where t is the corruption threshold. Now, in order to make such a classical way of doing secret sharing-based MPC protocol achieving scalable efficiency, the existing literature mainly has developed two kind of techniques for achieving this kind of efficiency. The first technique is the so-called packed secret sharing scheme, which introduced by Berkley and Young. The other one is so-called Vandermonde randomness extraction, introduced by Damgard and Nielsen. In this work, we developed a suitable counterpart of these two techniques to facilitate the designing of our protocol. To just give you a look at of what you're going to expect in the next few slides, first, for the packed secret sharing schemes, we designed something called what we call an unpacked secret sharing. And for the random matrix extraction techniques, we require something called a high dimensional, which we proved a high dimensional smudging lemma for proving the security of performing this kind of random extraction for our unpacked secret sharing. Okay, so now let's get into these two techniques. First, when you look at when you do this circuit emulation gate by gate, suppose here you have two secret sharings, one a secret sharing of X, one secret sharing of Y, both, let's say, shared by Shamir secret sharing. Let's say if you just want to do one gate emulation where you want to, let's say, add these two secret share up. Notice that here you're just trying to emulate one gate of the circuit. But the overall computation done by all the parties, each party locally needs to add up their own field elements. So the collective computation complexity for just emulating this one gate is n field operations. So this already introduced an overhead of n if you just naively use a Shamir secret sharing to emulate the circuit gate by gate. So note here that if it's an addition gate, you don't even need communication, but still on the computation side, you still has an overhead of n. So here comes the why we need a packed secret sharing. So packed secret sharing has this idea that instead of using one Shamir secret sharing to just share one secret, you share an order of n many secret in one instance of secret sharing. And by doing so, when party locally add their secret share up, even though they are still doing n many field operations, they are also emulating order of n many gates from the circuits. So this reduced the overhead from order of n to a constant overhead. However, the usage of packed secret sharing also has some limitations. This is because when you use packed secret sharing, you inevitably has to emulate multiple gates at the same time. And all these gates has to have the same type. And to overcome this kind of limitation when you design MPC protocols use packed secret sharing, existing works have developed different kind of method to make the protocol compatible with packed secret sharing. However, all of them fell short of achieving computation scalability for general circuits. So just to summarize, the key point of the packing usage here is that we want to achieve a secret sharing where basically the rate of the secret sharing schemes is constant. So by rate, I mean the cumulative length of all the secret being shared over the total share size. So here, when you are sharing order of n many secret, this rate of the secret sharing is constant. And the drawback or the limitation of packed secret sharing is that you are only achieving this efficiency in an amortized sense. You have to put many secrets together and then achieve this constant rate. So in order to bypass this limitation of packed secret sharing, what our idea is that can we design a secret sharing schemes that is MPC friendly such that it has a non-amortized constant rate. If we can design such, and hopefully we can do so by breaking a very, very long secret into smaller secret shares such that the total share size is comparable to the secret size. And if we can do so, then we don't need to emulate multiple gates at the same time, the limitation imposed by packed secret sharing, where we can emulate a single gate at one time. And the question is whether we can achieve this or not. And this is, for achieving this, we use a recent a tool introduced by one of our recent works, which is how to use Chinese remaindering theorem-based secret sharing schemes to design MPC protocols. So the key point about the prior work is that they show that this CRT-based secret sharing schemes is also compatible with the existing framework of designing MPC protocol in the sense that you can emulate the circuit gate by gate, and whenever you have a multiplication gate, you just do a similar degree reduction protocol. So I won't go into the detail of this, but just to give you a rough idea of how we can achieve a rate one constant rate secret sharing schemes. So the rough idea of how you share a secret in CRT basic secret sharing is the following. Suppose you have a secret small s from the field. Instead of like Shamir secret sharing where you re-random it as a random polynomial, here you re-random it as a random integer that equals to s modulo p. Then what you do is that you give each party this secret integer s modulo some pi. So each party has its own modular pi that you can think of them as distinct primes. Now the point is that the CRT secret sharing allows you to pick this P1 to Pn arbitrarily so long as they are co-prime. So you can potentially pick each Pi to be, let's say, P1 equals to 2, P2 equals 3, and so on. So the share size of each party can be as short as, let's say, just 1 bit, for example, if P1 is 2. And if you pick P1 to Pn appropriately, you can achieve a constant rate for the secret sharing schemes. And a few remarks about this, that first you can see that if I do want to achieve rate 1, the secret size has to be at least linear in n because the total share length has to grow with the number of parties. And this is inherently why our protocol will only work if the field size is exponentially large. Here it doesn't need to be quadratic in n, but shortly, the next slide we'll see why it will be n squared. And also, here is why we have to measure the complexity of our protocol at the bit level, because here each party is operating in a different field. So in order to measure the complexity, we have to go all the way down to the bit level and add them up. And finally, if we are given, remember that for the degree reduction protocol, we need a sharing of some mask R that for doing the degree reduction. If we are giving such masks, then this simple idea already enables us to achieve scalable MPC for the entire protocol. So the question remains how do we generate this random mask in a scalable with scalable efficiency? Well, note that first, we are going to consume one pair of masks per multiplication gates, and therefore, in order to maintain that per gate complexity doesn't grow with the number of parties, we have to make sure that each pair of this random mask is generated without the complexity depend on n. However, for security reasons, no single party can generate such pairs, so each pair should have contributions from all the parties. So how do we resolve this conflict? So this is a standard trick introduced by Damgaard and Nielsen in 2007, which roughly has the following idea, that you're asking each party to generate a pair of their masks. You know that out of this n mask, at most T of them are maliciously are corrupted from corrupted parties, and the rest n minus T are from honest parties. So you are going to extract n minus T secure masks from these out of this n random masks generated from all the parties. And here, what Damgaard and Nielsen show is that suppose as long as the matrix V that you are using here to do the random extraction satisfies something called super invertibility, which basically means that any square submatrix, any n by n minus t by n minus t square submatrix is full rank, then you can show that the extracted masks are indeed secure against any t subset of corrupted parties. So this is basically, the reason is basically that when you have a vector of random field element, if you multiply by a full rank matrix, you will again get a random field element, which can be used as a perfect one-time pad to mask anything you want to mask. So now, the natural question is that can we use this randomness extraction trick also for the CRT secret sharing? What are the barriers there if we want to directly use it there? Note that the key difference here is that the random mask being generated, the R1, R2, and Rn, these are distributions over the integers. Remember that for CRT secret sharing, these are secret are re-randomized as integers. When you reconstruct secret, you first reconstruct integers. This is unlike Shamir secret sharing where you reconstruct polynomials. So because of the fact that these all the random masks are distributed over the integers, what we are essentially trying to do is do a random extraction over the integers. And this is not an easy task to do. So I won't go into too much detail about how to do this, because I haven't even tell you what the distribution of R1 to Rn looks like. Instead, what I will going to do is that I will going to show you some toy examples, and hopefully will give you some idea why this might be hard. So let's look at this toy example. Suppose I have a uniform distribution I call UN, which is over some 1 to m, uniform over this consecutive integers. Suppose they are exponentially domain. And what if I use 2 times of this random integer to mask the secret, whether on one hand the secret is 1, on the other hand the secret is 0? Is this a secure way to mask the secret? Well, my slide already leaked answer. The answer is no. And the reason is very simple, because if you look at left-hand side, they are only supported on odd numbers. If you look at the right-hand side, they are only supported on even numbers. So of course they are disjoint. So this cannot be used as a secure mask. Now let's go one level more complicated. Suppose I have 2 such masks, UM and UM prime, and I use some matrix here, 2, 1, 1, 2, to extract some random masks to mask these 2 different vectors of secret. On the left-hand side is 1, 0, on the right-hand side is 0, 0. Is this a secure way to mask the secret? Well, again, like my slides show you that they're not, but this is harder to see compared to the previous one. But if you sit down for a while and stare at it, you will realize that they're again supported on destroying, their support is destroying. For example, you can see this by, let's say you take the 2 times of the first row minus the second row, and if you modulo 3, you will find that the left-hand side and right-hand side are different. So this is just to show you that even though this matrix could be full rank modulo P, when you are looking at things over the integers, they could very well be very far apart, these 2 distributions. So our key observation here is that as long as you can ensure that the secret you are trying to mask, if you look at their difference, if that difference is divisible by the determinant of this matrix you are used for extraction, then it will again be secure. So here, for example, in the one dimension setting, the matrix is just 2. If you mask to any secret that is divisible by 2, then it will be secure. In the second line, because the matrix has a determinant 3, if you mask any 2 pair of secret where their difference is divisible by 3, then you will again be secure. So I won't prove why this is true, but hopefully you can see that this already eliminated the attack that I mentioned earlier. Okay, so if you work on this idea, and you will basically, this is what we get, that suppose I use a van der Waals matrix. In particular, we are using this particular van der Waals matrix here to extract the random integers used as a mask to do the degree reduction. Then as long as I can ensure that the difference between the secret I'm trying to mask is divisible by this quantity, which is basically the determinant of the van der Waals matrix, then I can ensure that the protocol is secure. And then the main point I want to say here is that this determinant of this van der Waals matrix is an n² bit integer, which is why our final protocol is only provably secure when the log f also grows with n². However, I think this is only a proof techniques. I don't see why this is inherent, and maybe a better analysis will bypass this barrier. So yeah, okay. And with that, I will end my talk here.